Hello everyone, this is video 15.3 and .4 kind of all together. Just taking a look at some of the class notes. First thing that we're asked to do is to briefly describe the Rutherford experiment. Now, the Rutherford experiment essentially had us taking alpha particles, shooting them through gold foil, and then recording where they scattered. Now, here you got an alpha particle source. You're kind of isolating the source through lead sheet with a hole. Now, most of the alpha particles came through, forming that pattern of green, but occasionally one's even bouncing back. And so what is the major conclusion here? Right, that is the major procedure, but he's concluding that most of the space is actually made from empty space, and you've got this very dense nucleus in the middle, which would allow for electrons to bounce back. So he concluded that a nucleus made the most mass and least volume. Of the atom. Bohr's model of the atom really focused in on the electron shells. Now, essentially what's happening here is you're taking energy as they get absorbed in, and you can see that again. As energy comes in, you're going to see the electron move up. Right, as a photon, it's going to move in the electron orbit up. Right, see, it's now moved here and here, and then gets released. And that's essentially the Bohr model of the atom. So as we take a look at the energy running through the Bohr model, it's helpful for us to have a reference point. Now, this diagram here shows the reference point as being what we call n is equal to 1, or the ground state. Now, most often we don't actually see the ground state as being energy level 0. We usually kind of go free electron as being 0 electron volts. Now, if a free electron is, and here's my nucleus, if that is 0, then these levels below wind up having levels of negative energy because the electron gains energy and moves up to a higher orbit. And so this might wind up being something, let's say, like negative 13.6 electron volts as they drop down. For the example, we're going to keep using the the ground state as a reference, but the difference in energy is really the point, and whether it moves up or released depends on whether it gains or loses. As it moves from N1, and as it moves up, N2, N3, N4, 5, and so on, this is still 1, 2, 3, 4, 5, and so on. But here, going from 1 to 2, if that's 3.2 electron volts, then this level here would be negative 10.4. The next state would be negative 5.2 electron volts, and so on until you reach 0. The difference is the same here. Between 1 and 2 is still 3.2 electron volts. Between 1 and 3 is still 8.4 electron volts. It's just our values are different. So let's take a look at a few examples here. What is a wavelength? if we transition from the first to the third. So going from the first to the third, that means that 8.4 electron volts have been absorbed, right? So it has been absorbed because it's moving up, and as it's moving up, the electron is gaining energy and absorbing it from that photon. E is equal to hc over wavelength, or the wavelength is equal to hc over E. Now for h here, we're going to use the 4.14 times 10 to the negative 15. C is just 3 times 10 to the 8. And the reason why we're using 4.14 is because we've got 8.4 electron volts, so we're keeping everything electron volts, and we find that is going to be 1.47 times 10 to the negative 7, which is in the UV band. The next one says, well, what if we're going from the second to the third orbit? So if we're going from here to here, well, the difference is just 8.4 minus 3.2. That means 5.2 electron volts are going to be, again, absorbed because we're going up. So using the same formulas as we did before, only thing that changes, instead of us having the 8.4, we're going to use a wavelength energy of 5.2 electron volts, which gets us a wavelength of 2.38 times 10 to the negative 7 meters. Again, that's in the UV range. Taking a look at the next one, we're looking at going from the fifth to the third. So we're going from 5, 4, 3, doing this one in blue. That difference there is 12.3 minus 8.4. That gets a 3.9 electron volts. Same numbers again, except for E, we're going to use that value of 3.9 electron volts. So we wind up with a 3.18 times 10 to the negative 7 meters, again being in the UV, but in this case, this is released. So this photon is going to be coming out, this UV photon, as the electron moves from the fifth to the third orbit, gets released. Taking a look at a couple more examples here, just two more. We're going from the fourth to the third, coming from here. So the difference means that we've got 3.3 electron volts. Right, as a modification. So again, using 3.3 electron volts here for E gets you a wavelength of 3.8 times 10 to the negative 7 meters. And again, because this is moving down towards the ground state, this is going to be released. This photon is coming out. So if we're going from the first to the fifth, coming on up all the way here, we've got hc over E. The amount of energy is going to be 12.3 electron volts, and you wind up with 1 times 10 to the negative 7 meters. That's UV light, but again, this is going to be absorbed. Okay, if you got any questions, let me know. Thank you.